Hi, and welcome to the AP Biology Lab 2 walkthrough. This is on enzyme catalysis. This is actually the first lab that we do throughout the year. Some of the diagrams that I have here, this is actually hydrogen peroxide. Hydrogen peroxide is going to be the substrate that we use in this experiment. Here's some yeast. Yeast contain an enzyme, most living things do contain an enzyme called catalase, and the function of catalase is to break down hydrogen peroxide into water and oxygen. And so before we get too far into that, let me give you a demonstration. And so what I've got, actually let me go back for a second. So in here I've got a beaker, and then in the beaker I'm going to add a little bit of yeast. So if I put yeast at the bottom, so now we've got some yeast in there, and I'm going to add a little bit of hydrogen peroxide to that. So hydrogen peroxide contains the substrate, so it's a chemical that's going to be broken down, in this case by the catalase inside the yeast. And so if I pour a little hydrogen peroxide in there and mix it up, then eventually what you're going to get is it's going to start growing inside the beaker. And so what's growing inside the beaker is the yeast breaking down the hydrogen peroxide. They're converting that hydrogen peroxide into oxygen and water, and that oxygen is being given off as oxygen bubbles. And so you can see that it's eventually going to move up and over the top. Now, as it does that, the amount of oxygen eventually increases more than the beaker itself, so it flows over the top. But the beaker itself feels kind of warm to the bottom, and so at this point we can see that energy is given off from that as we break down that hydrogen peroxide. And so you need to remember those two things. You need to remember hydrogen peroxide, and then you need to remember catalase. So what is an enzyme? What is a substrate? And so an enzyme looks like this. An enzyme is a chemical, it's a biological catalyst, and it's always a protein, and what that protein does is it breaks down another chemical. Now in chemistry you should have learned that a catalyst is part of a reaction, but it's not technically part of the reaction itself. In other words, it's not broken down. And so in this case what we have is a enzyme which is called catalase that's sitting inside the yeast, and the hydrogen peroxide will fit into that enzyme inside the catalase, and what it does, it breaks it down. And so in other words, in this diagram here we have a substrate, a chemical that fits in. It then tugs on that substrate in some way. It makes a microclimate inside that enzyme, and what it eventually does is break it down. So in this case it breaks it down into two things. It breaks it down into water and then oxygen, which is given off. Okay, so in this lab, the lab setup is fairly simple. What we did is we punch out chads, or we will do, is we punch out chads, which are little discs of paper. We then dip those in a yeast solution, so we know the concentration of the yeast solution, and then we simply put it in a beaker of hydrogen peroxide. Hydrogen peroxide then, imaginary hydrogen peroxide I'm holding right now, the disc will sit at the bottom, but as that enzyme starts to break down the hydrogen peroxide, little bubbles will start to build up on the outside of that disc, and eventually it floats to the top. And so we can put a number of discs in there, and then we can measure the rate just by the time it takes for it to float to the top, by measuring the amount of oxygen that's built. In this lab, our independent variable then is the concentration of the enzyme. In other words, how much enzyme is actually added to that disc. We then measure the rate, and so the faster that disc floats to the top, that implies that it is a faster rate. In other words, the smaller the distance, or the smaller the time is, the faster the rate. And so when we graph it, we have to actually do an inverse relationship. In other words, our independent variable is the concentrations. In this case it's grams per liter, and so we put that on the x-axis, and then we put the floats per second on the y-axis. What are floats per second? It's one float divided by the time it takes for that disk to actually float to the top. And so what we get is a relationship where as we increase the concentration, we also increase the rate of enzyme breakdown, or the rate of that reaction. Now eventually, if you can play this out a little bit, you can see in the data here that eventually it's going to move up to a point where it levels off. In other words, it's not going to go any faster than that. And so why is this all occur? In other words, why is it that we are increasing the rate of reaction by increasing the amount of the enzyme? Well, think about it this way. The enzyme just sits there, and the more substrate molecules that can come to that, then the more likely it is to break those down. So by increasing the number of enzymes, we can increase that respiration, or excuse me, that rate of catalysis in this case. So again, the equation that you need to remember is that we're breaking down hydrogen peroxide into water and oxygen, and catalase is our enzyme. We can measure the rate in this experiment it by either measuring the amount of products, and that's what we do by measuring the amount of oxygen bubbles that are created, or we could also do it by measuring a decrease in the reactants. The rate is then equal to the slope of that line. And we just measured one thing. In this case, we just measured how the concentration of enzyme affects the rate of this reaction, but we could have measured temperature, and what would that do? To think about it for just a second. If we increase the temperature, the molecules are going to be moving around faster, and so that should increase the rate of the reaction. What about the pH? We would find that the pH is going to increase, and you can see that right here in this actually is a diagram of temperature, but the effectiveness of that enzyme will increase to a point where it'll eventually drop off. In other words, as the temperature increases too much, then that protein is going to start to denature, and so it can't work as well. Same thing with pH. Each of those enzymes has a specific pH that they function at, and so if we go much beyond that, then we're actually going to start to break down that protein or denature it, so the reaction is going to slow down. But also we could have measured the rate of the change the concentration of hydrogen peroxide and measure that, but in this case we just measured the enzyme. And so that's enzyme catalysis, and I hope that's helpful.